Okay, so yes, I talked about these Heisenberg algebras and Clifford algebras and things like that. Let us just now talk about Nakajima basis. So if I write here, this is our line. Okay. So yeah, so let's just talk about cohomology weighted partitions and Nakajima basis. And Nakajima basis. Okay, so we are going to discuss about these operators that we defined last time. So let's do this. So in some sense, I would like to discuss correspondence between Heisenberg or Clifford algebras and focus space forming them. Cohomology theory of Xn, which is the Hilbert scheme of endpoints on a given quasi-projective variety X. Okay, so let's start by let X be a quasi-projective surface for now, because we actually would like to study Hilbert scheme of surfaces anyway, and now fix some integer I bigger than 0, and we would like to define a cycle. Define a cycle, which I'm going to call P bracket I. It's a cycle in direct product of co-product of these many factors of Hilbert scheme of n minus I points on that variety times n. It's defined the following way. So definition of PIs is given by the set of, remember that the Hilbert schemes are moduli spaces parameterizing ideal sheaves, especially for these ones. These are ideal sheaves of points on that surface. So this is going to be given as sum of union of sets, set theoretically unions of pairs of I1, I2, such that these are points in here, such that I2 is a sub-sheaf of the ideal sheaf I1, and support of this module, which is a zero-dimensional module. It's a module, it's a sheaf with zero-dimensional supports on your surface. The support of this thing we would like to be one point only, X, with some X in our surface. Okay. There are, after all, some cycles that you can construct this way. Okay. Similarly, for I less than 0, we just need to swap. We just swap the place of I1 and I2. Okay. Now we can define a morphism So define a morphism. We call this morphism big pi from this cycle pi to x. Now I need to tell you what the morphism does to the pair of ideal sheaves on that surface. So it does take a pair of ideal sheaves which satisfy that condition to basically x. Little x, which is inside the surface. It just forgets the sheaf information and sends the pair to the point in the surface where the quotient is supported at. It's the punctual and the hidden. So now the dimension of restriction of this cycle, intersection of this cycle, basically this product, dimension of this is given by okay, so what's the formula? So let me just see, can we, yeah, it's okay, so we can see it. The dimension is given as follows. So complex dimension of this cycle pi is equal to intersected with this is equal to 2n minus n plus 1. You can investigate whether this is true or not, but I'm not going to go through it. Okay. All right, now we pick two cohomology classes. Now for alpha and beta, elements of cohomology theory of X, the rational coefficients. Now this is going to be, we would like to, right now we talk about cohomology theories. There are really going to be Borel-Moore cohomology classes, and later there will be just equivariant cohomology classes, because for instance when we work over some C2 or something like that, then we would like to take the equivariant cohomology with respect to that action of the torus. So for alpha and beta, for suitable cohomology theory of X, Borel-Moore, for instance, we define P alpha of I, which is going to be pullback. It's a cohomology class. It's the pullback via this map pi. The pullback of alpha intersected with the cycle, with the cohomology class of cycle. Okay, and this thing lives inside. This thing lives in product of cohomology theories of xn minus I times, for instance, like a locally finite or Borel-Moore cohomology theory of X. So this Borel-Moore cohomology is the cohomology theory of possibly infinite chain complexes with finite support. Okay.
Sorry, what is that, LF?
Locally finite, the Borel-Moore. Yes, so this is basically that. And then I can also define something for, so here we are thinking of, I think I haven't written it, but here I'm assuming I is bigger than 0. And I can also define something for negative I.
So when you write I alpha star, you mean pull it back to to PI.
to
right?
PI.
Okay.
Right. Okay. So remember that PI is actually a subspace of the product of these two guys, so it has a cohomology. And also I can define something for another cohomology class, P beta of minus I. I can define this as pullback of beta intersected with P minus I. And now we know what P minus I means, because we know for negative integers how should I define it. And again, the element in here, since I assume my I is positive, now minus I, that would be n plus I. So we find homology. Okay. So what are these really geometrically speaking? These are P alpha I and P beta minus I are realized as I realize as the cohomology classes. Homology classes of set of, let's write it like this, I1 quotient by I2s, such that the support of I1 mod I2 is given by X for X belonging to the dual, the cycle given by the dual of homology classes alpha and beta. So you have something like that, you have some cycle alpha, let's say, like that, and you're looking at the space parameterizing zero-dimensional subscripts of length n, for instance, on here, and you're looking at these pairs. I mean, you're looking really at the product of these two things. You have the pair of ideal sheaves, and the quotient of them is supported at a point, which lives on the cycle. And this is obviously, you can actually see, is already very important, this kind of point of view, because when you count curves inside the Hilbert scheme, you're mapping the curve, and you would like to map the marked points on the curve to certain points in the Hilbert scheme, and those points will be parameterized by cohomology classes of the cycles they live on. And that's how you do curve counting inside the Hilbert scheme. Okay, so that's that. And then this means that P alpha I or P beta minus I live in cohomology theory of xn minus or plus I times cohomology theory of xn or homology, depending on bias orthogonality. Okay, this just follows by definition. Okay, so what is this now? What is the main theorem? The main theorem is the following theorem. This is due to Nakajima and Gronowski. that the following relations hold true. Relations hold true. First, oh, by the way, these cohomology classes, inside the product of these things, they can be thought of as operators on cohomology series of Hilbert scheme of n minus I or n plus I points and Hilbert scheme of n points. So basically, you can think of these guys. Maybe I should write this somewhere.
Theorem of kind
Some sort of operation, operators. Yeah, kind of similar.
Pull back and
Yeah, pull back and push
forward.
forward. Exactly. Exactly. But in the level of cohomology, yes. Yeah. I can think of, for instance, this or this as a map from cohomology theory or homology theory of Xn to now, depending on which one I put first, if this is plus I, then that will be minus I. So these are operators that take you from cohomology theories or homology theories of these Hilbert schemes of different number of points to each other. And as you mentioned, yes, they look like Fourier type transforms. You pull back the class and then you push forward to the other cohomology theory. And they satisfy a structure as follows. So there is a bracket between them that you can define, which satisfies the following condition. I minus 1, I times delta I plus j and 0 alpha beta times identity. So maybe I should okay. And second relation is that you can. So here's the condition. So this is if minus 1 to the degree of alpha, degree of beta is equal to 1. The second relation is that the bracket between them will be minus 1 to the I minus 1I delta I plus j and 0 alpha beta density did I make a mistake? There's something I'm missing in my formula. Okay, so I don't know what should be the modification. Do you have it?
I'm checking.
Yeah,
What's it called? It's Nakajima.
Yeah, Nakajima-Granovsky. I think there is some term that is wrong here. So this is otherwise, but one of the terms is not wrong here. So
I'm trying to find it. How do you spell? Do you know
If you just look at, let's just look at the book of Kojima. There's no points on lectures on. Yeah, yeah, that one. No, more left. No, there's no points on. Yeah.
I'll let you know when I find
Okay.
it.
So let's just.
Are these two equations the same?
Yes, yes. There is some term that I'm missing in here.
I'm looking it up right now. Do you know which page?
Yeah, go to page 80. 80. Yes, go on.
It's two different brackets.
Yes, yes, yes. One of them is the. Which one is not a bracket? Okay, let's discuss this. I need to figure this out, but still are brackets. But let me just show you what this does actually to these cohomology classes in an example that we can see it actually. Here, by this thing, we really mean intersection pairing of alpha and beta, which is defining to you a map from X to the point. Okay, the difference is actually different bracket. That's something subtle. I forgot to include the detail of. But anyways, we can fix it next time. Okay, so now let's do one example, so that at least an example I can show you what these operators do. Example.
I think the curly bracket is the one for the Clifford algebra.
Oh, it's the Poisson bracket that we defined for the Clifford algebra. I see. Or the bracket defined for Heisenberg actually. Is it Clifford?
So the square bracket is the one for Heisenberg.
I
The
see.
curly one is the one for
For
Clifford.
Clifford. I see. Clifford. Okay, good. Now it's much better. Yeah. Okay, yeah. So this is actually very subtle. It actually relates simultaneously both Heisenberg algebraic structure and Clifford algebraic structure to the cohomology theory. It's very interesting. Okay. Yes, we are going to use this Heisenberg algebra correspondence anyway, so later. So fix a point. Let's do an example. Fix a point. And yeah, both these Heisenberg and Poisson, Heisenberg and Clifford brackets we defined last time. So they are a tiny bit different. Yes, so fix a point, let's say x inside x, and set I equal to 1 and j equal to -1. Let us fix cohomology classes of alpha and beta 1 to be fundamental cycle of x, and let's say beta to be equal to point class for that point x. Okay? Now take distinct points. Let's call them x1 all the way to xn, and let J be the ideal of those things. So these are, by the way, these are distinct points, distinct from the point x. And let J1 be the ideal. So this is ideal of these many points. So functions vanishing at these things, and these are different from the point x, we can calculate. We can calculate this bracket, the Heisenberg, P alpha I, P beta J. And these are operators. Remember that these are operators, then this is a commutator between the operators, and that acts on J1. And we would like to see what that is. Okay, so so we would like to, so let's just calculate it. So first, let us see, let us note that P of little x minus 1 acting on J1 is, okay, so what does this do? This adds to the, it's the operator that sends you from the Hilbert scheme of n points to Hilbert scheme of n plus 1 points, such that the co-support lives on this x variety given by x, which is x. This is the class of x, little x added with union of J1. Then we can also, if this is the case, then we can basically see what is the product of these two operators. If I look at the product of these things and then act on class of J1, that is the sum of cycles of the form so little x union J1 missing a point. Do you agree? Because this removes a point. Okay? And i.e., this is equivalent to saying, let me bring some chalk, by the way. White chalk. Yeah, that was a very subtle point that I didn't pay attention to. The Clifford bracket gives you 1 Heisenberg bracket gives you 1. Okay, so this is the sum of cycles of this form minus a point. And why is it the sum of cycles? Because first you look at the configurations of points given by J1. These are ideal Schiffer functions vanishing on some many points, n points. And this thing adds a point to that configuration, and then you remove a point, but then you can remove any of the things, any of the possible points. So you have n plus 1 points in here, and you can remove many. Okay? So basically this now tells us that if I act on like P big X 1, p small x, maybe I should write it as curly x so that it's not confusing, minus 1 by j1, this will be the cycle of x1 to xn plus summing over I1n of x added to x1 all the way xi missing from the group like that, and this sum is over I. Yeah, that's obvious. So you first add a point to that n many points. If you have n plus 1 points, now you're removing a point, and you have the option of removing n many options of removing the point. And plus n. Okay, so that's what it is. And similarly, we define what is this operator, p of little x minus I, acted on p of big X plus 1 of j1 will be. So this will be p of x of, degree minus 1. And, well, again, what does this do? This is in degree 1, so it's an operator from Hilbert's scheme of n points to n minus 1 points. So, but in this class, that means that you can, in principle, remove a point anywhere you want. So this is the sum of cycles again. So this becomes, again, sum of cycles. X1 to xi missing xn. So again, if you actually do the calculation, now that you have this thing, and these points are distinct from this point x, this just becomes sum over 1 to n of, the cycle corresponding to x, which is its distinct point, union this set. Okay. That's what it becomes. Now, as you can see, we have the same. Okay, so we don't have the same. What do we have? You can see that the difference of the two becomes something that you recognize. It's the cycle given by J, associated to the ideal sheet, or J1 or I1. Okay, so this hence we conclude that actually the alpha I, the beta J, in this case acting on J1, which is equal to dx, this is the big X, P little x minus 1 minus little x minus 1 dx1 acting on J1 is equal to J1. Okay, so I think, let's say, for instance, n is equal to 4. What did we do? We were looking at Hilbert's scheme of functions vanishing at n distinct points on this surface, x1, 2, 3, 4, and then we can apply P of little x minus 1 to this thing. Given that little x is distinct from these points, what do we get? We will get x1, x2, x3, x4, and a distinct point x in the middle. And then we can act on this by this operator, which removes one point from the configuration but doesn't care which point. So what do you get? You will get many possibilities. So these are those cycles. So I can get something like this. I remove this x2, or I could get, I remove x1, like that. Or I can just remove the point in the middle. This is the set whose cohomology class gives you the J1. And that's what we just started with. That's J1. This is J1. And I could remove x3. So this will be like this configuration. And or I could remove x4. This configuration. And basically, if I did now the other way around, P of x1, now I can remove points from this configuration of 3 points, and it's becoming the sum of cycles. I can remove x1, so I have x3, that configuration. Actually, these I can draw in yellow, like that, or I can get remove x2 like that, or remove x3, or remove x4. And you can see that if I add now px minus 1 to this thing, minus 1 to this thing, what do I get? I will draw these by, I think I will just get, basically there are 4 sets. I will get all of these things except the middle. Right? And that's the idea. So I will get this one, let's call it A, B, C, D. I will get A and B and C and D. And I will be left with this. So that actually tells you that the difference between these two operations actually becomes just J1. This is the way to actually calculate this in practice. But proof of it is involved, and we're not going to go. And yeah, I apologize, I didn't do it for the brackets because I was just always thinking about Heisenberg bracket, not the Clifford bracket. Sorry. Yeah. Okay. All right, so that's that. So this is an important theorem. And now let's talk about Nakajima basis for Xn. So Nakajima-Granovsky's correspondence gives you a correspondence between Heisenberg or Clifford algebra formalism and the cohomology theory of Hilbert scheme. So now let's assume that let us assume X is equipped with an action of the torus. So we can just talk about a covariant cohomology theory of Xn. Fix a basis. Gamma 0, gamma n of covariant cohomology theory, T covariant cohomology theory of X with rational coefficients, given a non-negative n, some number, some integer n, a cohomology weighted partition, cohomology weighted partition of n is as follows. So we would like to partition this number. This stands for the length of the zero-dimensional subscheme that the Hilbert scheme parameterizes. And we would like to say that this is partitioned into a bunch of n1, n2, n3, n4, such that their sum adds up to n. And we would like them to lie on different cycles of your variety. So we would like to partition this integer and label our partitioning by the cohomology cycles of x itself. That's what it means, cohomology weighted partition of n. Okay, so given a non-negative integer, the cohomology weighted partition of n consists of, okay, an unordered set of pairs. We call that the vector mu, which is a set of pairs mu 1, gamma I1, all the way to mu L and gamma IL, like that, where the set mu 1 to mu L is a partition whose parts are labeled by gamma and k. Okay? I mean, of course, this right now doesn't have any geometric meaning. It's just the partitioning of this integer n by some labels. Labels can be integers, can be real numbers, or can be given as functions taking values in cohomology theory of x. But later, this is extremely helpful because not only this labeling formally gives us a way of partitioning n, it also actually tells us where those clusters of points, of mu1 points or mu L points, where those things actually live. Where in the variety they are living. Okay. By gamma ik. Okay. So for a homology weighted partition mu, the associated basis element is given by. So now we are interested in defining certain basis elements for the equivariant cohomology of the Hilbert scheme of points. So every time that you give me a cohomology weighted partition like this, that defines for you a certain basis element in that cohomology, and that's basically given as follows. This is the Nakajima basis element for the equivariant cohomology of Hilbert scheme. So it's defined this way. The product from 1 to L of these operators that we defined, mu k. This is a number. Remember, this was a number. Actually, where did I put the number? I put it in the on the bracket, so I can do it this way. Yeah, sure, no problem. Comma ik. Like that. acting on the vacuum vector of this vector space. And I will tell you in covariant homology what this vacuum vector is. Divided by maybe something that, you know, maybe I write it like this, z of mu, where z of mu is just something that keeps track of the, you know, automorphisms of these configurations of points. So it's just product of mu k's times length of the automorphisms of the partition here. Now this is a constant number, of course. It comes out.
What's the term after the p? Like the last term?
Minus, that's the vacuum vector.
Oh, the vacuum vector.
So you have the operators and you have this vacuum vector in your cohomology basis. Basically the same thing that, if you remember, we defined the basis of the Fokker space and in the Heisenberg algebra and Clifford algebra by operators acting on the vacuum vector. And we discussed that these could be like creation or annihilation operators. So these move the state of the vacuum vector in the vector space. Okay. Now the cohomology degree of a basis element mu under, okay, so given a partition, we will get some basis element like this. Now this, I hope, is not a confusing notation that I would like to think of that basis. I would use the same notation for that basis element. So by this, really, I mean this object. So this is that. Okay, so the cohomology of this on the element mu under these identifications is its degree is given as follows. Okay, so its degree is given by is 2 times n minus length of our partition plus sum of the degrees of gamma ik's, which we use to compute, partition the integer n.
So just recap what you said.
So the length of partition.
So you really, those are basis of the equivalent homology of all the x's together.
That's right.
And you showed that, well, clearly you have operators that form a Heisenberg/Clifford algebra acting on it. Just trying to recall.
And
did we show that also?
And these things, yes, and these things generate the cohomology theory.
Yeah, well, I'm just trying to recall whether we showed all such representations must be high speed.
Yeah.
Okay, we did that already.
We did that. So, for instance, let us calculate degree of the following. I give you a partition of n. So let n be any number, and I would like to give you a partition this way. So I just choose partition of n to be 2 and 1. This is 1 in the covariant cohomology theory of x. This is the 0 basis element, 1, and then I give 1, 1, 1, 1. Okay, how many do I need to have? I need to partition n. So I would have n minus 1 many of these things in here.
Minus 2.
N minus 2. Okay. Now, this is sometimes also written as like 2, 1, and 1, 1 to n minus 2. This notation also is used. So if I want to calculate the degree of this guy, let's give this a name. So I give this element a name d. So degree of d is equal to 2 times n minus. What is the length of the partition? I have n minus 2 guys in here and 1 in here. So that is 1 minus n minus 1. That's the length of our partition. Is the number of the parentheses, basically, plus sum of degree of ik's. All of the ik's have degree 0. So that is 2. So as you can see, this defines for you a divisor class. So D, that's the name D. So D is the divisor class in a covariant homology theory of Xn. And does this make sense in terms of what we did before? Remember that in the Hilbert scheme of 2 points, there is a locus which understands when the 2 points come together, and they can, induce a point of multiplicity 2. And the Hilbert scheme is literally given by the diagonal of x times x divided by the symmetric action of the symmetric second group, the blow up of this thing along the diagonal, basically. And the diagonal exactly parameterizes the locus where the 2 points come together. And it's a divisor. This is that divisor, you see? And this is basically telling you that you have a point of multiplicity 2. So this is the topological divisor of the Hilbert scheme. In the case of Hilbert scheme of 2 points, we saw it. In the case of Hilbert scheme of n points, it's also true. So in fact, when we talk about quantum cohomology, the statement is that the quantum product with this divisor class produces the quantum cohomology of Hilbert scheme. Generates the quantum cohomology ring. Okay. So that's that. Yeah, so basically, that's the remark. We saw that x2 is the blow up of x times x divided by the second group, symmetric group along the diagonal x times x. And E, we call it E there, is the same as this D. Exceptional locus of the blow up, exceptional device. Okay. Now let's talk about quantum cohomology. Okay. Let beta be an element of second integral homology theory of Hilbert scheme. Be a curve class. Given cohomology classes mu1, remember that again, when I say cohomology classes given by these partitions, we know that to every single partition of n, we can associate the basis elements. So that's what we need. And so given these cohomology classes given by these partitions, an equivariant, T-equivariant cohomology of Xn with rational coefficients, the K point genus 0 Gromov-Witten invariant of xn is defined by integration as follows. So the same as the story as before, except this time our ambient variety, our target variety, is the Hilbert scheme of endpoints on this surface. Okay, is defined by integration against the T equivariant virtual class of the moduli space of genus 0 stable maps. Okay, so basically the k-pointed function mu1 mu k is, which is something on x of n, it's genus 0 k-pointed function with curve class beta is equal to the integral against this moduli space. Rational maps to the ambient Hilbert scheme where the image of the homology class of P1 inside the ambient scheme is beta. And this is virtual class. And basically, you're pulling back these cohomology classes, or cohomology classes induced by these partitions. That's the Gromov integral for the Hilbert scheme, where evaluation I from compactification of this moduli space, this is compactified moduli space, of course, xn beta onto the Hilbert scheme denotes evaluation.
So where's the dependence on I?
Hmm?
Where's the dependence on I? Those EVI maps.
So it, I mean, what is the dependence? What you mean?
Well, what's this map in particular?
Yeah. So it sends a map into this Hilbert scheme to the cycle in the Hilbert scheme whose cohomology class is gamma I. It's a dual to the gamma I. What's the map from P1 to Hilbert scheme mean? It's an ideal sheaf of points.
Right.
It's an ideal sheaf of points, basically lying in some locus of the ambient surface. So this is a tiny bit different type of evaluation map as we saw before. Right.
Just confused. Are those the same map?
Hmm?
The EV1, EV2, EVN, those are the same evaluation map.
You pick up different mark points.
Different mark points, right?
Okay.
Different mark points. And different mark points are basically being matched with different cycles inside X. So you have clusters of points, you have ideal sheaves on X, and the co-supportive ideal sheaf sits on the cycle which is dual to this cohomology class. K mark points. When I show you soon, in 15 or so minutes, when I show you the threefold theoretic picture, it's also nice because you can also view this, all of this picture you can view in a threefold. The idea is that you can view it better instead of thinking about maps to the Hilbert scheme as getting the honest zero-dimensional subschemes in the threefold. Right? So then we can construct to this n-pointed or k-pointed function, we can associate to this a partition function. So basically, the k-pointed partition function of these guys, which we can call just Hill, is the Hilben is the sum over all possible betas of mu1, mu k, or basically xn, sum over all possible betas of these things. And then I will need a formal variable that keeps track of these betas. And for that, I will take the degree of the curve class. So the power of my formal variable would be the degree of the curve class. And this divisor is exactly the topological divisor of the Hilbert scheme. The locus where the 2 points out of n points come together. Okay. So that's the partition function of these Gromov-Witten invariants. Okay. So then we can also define small quantum partition function, which just means the three-pointed functions. So small quantum partition function is basically given by xn is given by sum over beta of the following. Yeah. And this is the degree. Sometimes they write it as a d, and they, instead of beta, they add over the degree. Okay, so this is the small quantum partition. And what else? Okay. So now I would like to relate this to the threefold theory. So relation to threefold Gromov-Witten and Donaldson-Thomas theories. Okay, so by definition, so this is a remark, as we saw before, by definition, Xn is the moduli space associated to, Xn is associated to a functor, which we called Hilb n of x. It it was a functor, the moduli functor, which takes us from the category of the schemes over, in our case, complex numbers, to sets. So what it does is that for any scheme U inside this category, it takes U to the following family, takes U to Z X times U's, the zero-dimensional subschemes of this variety X times, of this scheme X times U, where Z is a closed subscheme, and we have the following commuting diagram. So we have this map pi, and then we have the projection onto the second factor U, okay? And pi is flat. In other words, Z is a pi flat family of zero-dimensional subschemes, of length n on X, parameterized by this family U. This is what the moduli functor does. That is natural. So in particular, now you can think of U being a rational curve isomorphic to P1. You will get zero-dimensional subschemes of X being parameterized by P1, but scheme theoretically, those are zero-dimensional subschemes in X times P1. And that's your threefold. Where, as you can see, this guy is flat. So as soon as U is equal to P1, you will get your threefold, honest threefold by functoriality of Hilbert's scheme. You will get zero-dimensional subscheme on here on the threefold. And this thing is fibered over the base P1, and it is flat. Because it's zero-dimensional, this is a finite map. Right? It's a finite map of length n. Finite map of order n, I mean. So imagine, in some sense, it is like saying that your P1 is being embedded inside your threefold, and you're getting some curve, some n-to-1 cover of P1, some curve with homology class n times P1, and you're distributing your points on this cover of P1, on the image of this curve. So that's the pictorially, that's the intuition behind relation between quantum cohomology of Hilbert scheme of endpoints and Gromov-Witten theory of X times basically the threefolds, P1, X times P1. So basically, yeah, so what is the picture I wanted to say? Now, we'll consider a projective line P1 with three distinguished points. Now we are embedding the P1 inside the Hilbert scheme, but we want this to be a three-pointed curve. So now we can fix the three distinguished points of P1. We think of these as mark points, and we map this into the Hilbert scheme. Obviously, this gives me some curve with homology class n times P1, and somehow it needs to see three cycles inside. This curve needs to meet three cycles inside the threefold, right? So the T equivariant Grama-Witten theory of P1 times X relative to the point 0, 1 infinity is determined by relative conditions mu1, mu2, mu3, which are elements in set of partitions of n.
Sorry, this terminology relative to 3 points.
Yes.
Exactly what does that mean? Yeah.
I will tell you. It means the following. So you have a variety X. You have a variety X like that. And let's assume that I fix a divisor inside this variety. We have the Grama-Witten theory of X, and this is something that last year I remember you were in the class.
So are you mean relative to the fiber over?
Exactly.
Okay,
Exactly. Then you know what. Okay. Yeah. So just to recap, we have this divisor D, and we can count curves inside the variety X, or we can count curves with relative profile against the divisor. That means that we are counting curves that meet the divisor transversely, basically, so to speak.
Yeah.
If the curve falls inside the divisor, which happens, actually tells us that the locus of smooth curves meeting the divisor transversely is open, and then you need to compactify this, modularize this. And the compactification is given by the presence of these bubbles. So you need to blow up the family and so on. There's some sort of normal cone construction of McPherson that you degenerate this variety over a family over A1 into the normal cone of D, and that's the bubble. So your curve, after construction of this compactified moduli space of relative curves, your curve meets your divisor transversely like that. And that gives you an enumerative geometry, which is called the Grama-Witten theory of your variety relative to the divisor that you fixed. Now in this context, your variety is a surface times P1, and we would like to define a notion of relative Grama-Witten invariance relative to these 3 points. So what that means is that we have the P1, we fix the 3 points, 0, 1, infinity, and we look at the fiber of our threefold on here. So we look at these fibers like that, and we can call these 3 copies of x0, x1, and x infinity. And now we would like to count curves inside here. The union of these things defines for me an honest divisor, and I can count curves with relative profile against this divisor. So my curve comes and meets these maybe like that. So it meets transversely. So this gives me a partition of n. mu3, that's the partition of it. mu1, mu2, mu3 belong to the set of partitions of n. So in some sense, counting pointed curves inside the Hilbert scheme of endpoints on the surface immediately gets related by factoriality of the Hilbert scheme, immediately gets related to relative, not the absolute, but the relative Grama-Witten theory of the surface times P1. And relativity comes from the fact that you're not just honestly backing P1 into the Hilbert scheme, you're putting conditions, and the conditions are given by mark points. So you have the mark points, you send them into the Hilbert scheme, and on the Hilbert scheme you fix cycles. you pull them back and you match the cycles with the mark points, and that's basically, in this geometric picture, these are basically the divisors that you get. Okay, so this is the correspondence between relative Gromov-Witten theory of threefold and quantum cohomology. Okay, so now theorem is the following. Theorem is actually, maybe I mentioned to you one of the first places, the first place actually that this appeared was when x was assumed to be c squared. So affine plane. Let x be c squared after a suitable change of variable which is going to be e to the I u equal to minus q. We know that the following holds true. So following relation holds true. So the minus IU n plus length of mu1 plus length of mu2 length of mu3. These are the partitions, the three partitions. Each one of them are partitions of n. Ah, well. So another thing that my picture's kind of bad, right? Remember that in the picture I show them like that, but you're embedding a curve into this Hilbert scheme of endpoints on the surface, and you match the mark points on the P1. These are the mark points on the P1. You match them with the cohomology classes given by partitions of n in the Hilbert scheme. All of them are partitions of n. The length of the partitions are different, but the length of the subschemes are always the same. They are all length n, except I can partition them differently. So it's true that in my picture you see 3 separate points and 2 points and 1 point in here, but at least in this picture this is telling me that this is some partition like this. And this alpha is the cycle where this point lies on inside this surface. So this is the Poincare dual of alpha. And this is a different cycle that these two lie on, and the length, sum of the length of these two, so these you can think of as points with higher multiplicity. The sum of the lengths is going to be n, and the sum of the lengths of 3 is going to be n. It doesn't mean that these are multiplicity 1, remember that. Okay. So you have that. Okay. So after that, but the length of the partitions are definitely different. The length of the vectors are different. So we can have LM1, mu1, mu2, like that. And this relative Gromov-Witten partition function, P2, P1, and C2, relative to this divisor, D0, D1, infinity. This is going to be, which partition function? N times class of P1 and with mu1, mu2, mu3. The image of your curve is like an n-to-1 cover of P1, and I'm distributing points on the 3 divisors on it. So this curve on P1 is n-to-1 cover. Okay, and this is going to be minus 1 to the n quantum small quantum product of these things. on Xn. Genus 0, 3 mark points. Yeah. That's it. 3 mark points. Okay, and this is the small quantum product partition function. This means adding all curve classes. All images, so all ends. All. Okay. So is it clear now how to relate the two pictures? Yes. So if you wanted to do Donaldson-Thomas theory, basically, so this basically tells you the 3 sides of the 3 vertices of a triangle, quantum cohomology of Xn, and the Gromov-Witten theory of P1 times X may be relative to some divisor, and the Donaldson-Thomas theory of P1 times X relative to some divisor. You can do the same thing by just viewing, instead of counting curves, you can be counting ideal sheaves of points in the threefold. Ideal sheaves of curves, ideal sheaves of curves with a given homology class n times class of P1 in the threefold, such that the ideal sheaf is given by the sheaf of functions vanishing along points with certain transversality conditions satisfied along the divisors. And we discussed about relative DT invariance. Did we discuss about relative DT invariance in this class? No, it was last year. Last year we discussed about what does it mean for a sheaf to be relative to a divisor. Again, it means that if that is the ideal sheaf, for instance, that precisely translates into the co-supportive ideal sheaf being transferred to that divisor. And that basically means vanishing of Tor1, of your structure sheaf of the curve relative to structure sheaf of the divisor vanishing. Basically, transversality for an ideal sheaf means this map being injected.
So for transversality for an ideal sheaf, it's the same thing as the transversality of the corresponding.
Yes. Oh. Okay. Basically, So. Yeah. Anyway, so I think this should be structure sheet. Anyways, it's the structure sheet. So pull up the curve also.
I'm a little bit confused because then,
Yeah.
but then why is the G of H equals dt like equivalence hard? Because it seems to me that they're counting the same kind of thing.
They are counting the same kind of thing, but remember that these are counting objects with different stability conditions.
Yeah, okay.
Ideal sheaves are always, over the coarse moduli space, they have no automorphisms. Ideal sheaves are objects, simple objects in their own algebra, so they have C star automorphisms, and so their stack is always Artin, but the coarse moduli space forgets the C star many automorphisms, and over the stable locus you have no automorphisms. So they, But the curves have finite automorphisms, and you're dividing by these cardinality of these automorphism groups. So it is a big deal actually to prove something like that. Now, why did I mention this? Is the following, which is really phenomenal. Actually, I'm not sure about the history behind this because I wasn't understanding these things when these were happening. I was actually in high school probably, and so the thing is, probably I think this was kind of maybe historically the reason that people started thinking about Gromov-Witten versus Donaldson-Thomas correspondence. Maybe one of the reasons at least. Interestingly enough, this side, this edge of this triangle is now completely almost proved. So for all toric varieties, it's been proved. For x being toric variety, it's proved. Not this x, but threefold. This is a threefold. Toric varieties for complete intersections in an ambient projective space, for instance, it has been proved. So this thing always holds true, this edge. These, on the other hand, we don't know. We know that for C2 it holds true. For affine plane it holds true. So these two sides of the triangle. We know that for resolution of AN singularities it holds true. That's the beautiful paper of Oblomkov and Malik. But for many other surfaces we don't know. If we pick X to be some local surface, local curved surface, like something like a Hirzebruch surface, like an or something like my O minus n bundle on a P1. We don't know whether this is true. In fact, I actually don't know if X is not symplectic, then what should we do? A lot of this business actually has to do with the concept of reduced Gromov-Witten theory and reduced Donaldson-Thomas theory. So the variety, for instance, for C2, the variety is symplectic and the Gromov-Witten invariants vanish. And so you need to reduce the Gromov-Witten invariance. So the correspondences are between reduced Gromov-Witten partition function and integration over the reduced virtual class. And basically, I don't know what happens when X is not reduced. X is not symplectic surface. Okay, so that's that. And we have 10 minutes. Let me just say something about basically just setting up the formalism to prove a statement like this. And we will be spending some sessions on this from now on. We would like to discuss how to prove this thing so that we can actually discuss it over non-symplectic surfaces. So, Nakajima basis. This was for any quasi-projective surface with a torus action. We can discuss this over the C2. So, Nakajima basis for Hilbert scheme of endpoints on C2. So a natural basis of C star square covariant homology of C2, Hilbert scheme of points on C2 with rational coefficient, is given by vectors. Now we can just use a covariant cohomology of C2. So I'm going to use these vectors. As you remember, every partition of n gives us a basis element in the Nakajima cohomology theory of that Hilbert scheme. So we call this thing zeta, which keeps track of the automorphisms of these points, and we call this thing I alpha minus mu I, acting on the vacuum vector. Index by partitions of n, where we defined what this z mu was. So why am I saying this again? It's not a repetition of the last one. The reason I'm saying this is that a covariant cohomology theory of C2 is very easy. Everything is written with respect to the character of the action of the torus, and the only torus fixed point in C2 is the origin. So a covariant cohomology theory is very, very easy. For instance, if I want to write down a covariant cohomology class of, let's say, this is C2, then, this locus as a class, one of the lines, and this is just C2 times class of C2. And a covariant cohomology class of, for instance, the origin That's just a monomial that vanishes on that origin times class of C2. So these are examples of the generators of this equivariant homology. So here we don't have many choices to choose those gamma i's, which label our partitioning of N. Instead, we extend the cohomology ring into a cohomology ring, into a polynomial ring in variable T1, T2 with coefficients in the equivariant cohomology class. And then we realize all cohomology classes by taking advantage of these monomials in T1 or T2. So that's what we want to do. So let L of mu be the length of partition mu, the Nakajima basis. Nakajima basis here is basically is defined by as before. Defined as this is what I mean. So you can look at the covariant homology theory of Hilbert scheme of endpoints on C2, and it's naturally identified by tensor product with a polynomial in the equivariant character T1 and T2 of the Fock space. So this is the Fock space whose elements are these creation or annihilation operators, and naturally, saying that I'm labeling my basis of cohomology with partition weighted by cohomology classes, covariant cohomology classes of C2 is naturally, in this case, as easy as this. Basically, we are extending this cohomology theory by over Q by polynomials in T1 and T2. So in this case, it becomes very, very easy. And again, the Nakajima basis element corresponding to mu is mu i's. G of mu, where G of mu is cohomological dual. Cohomological dual to the class. The class of sub variety. Subvariety of C2 and with geometric element being given by, oh, well, we can write it like this. Like that. The geometric element being given by union of schemes of length mu1 all the way to mu of length of the vector mu supported at L length of mu many distinct points of C2. Okay, this is exactly what we have done before. It's almost a repetition of the previous one, except here I'm just saying that homology class is weighted by the partitions take an easier form in here because now I can extend my ring by this easy polynomial ring in T1. Okay, and so here, by the way, so here the vacuum vector, which you asked about, vacuum vector, the vacuum corresponds to a unit in the covariant cohomology theory of Hilbert scheme of 0 points on C2. Which is the TF covariant cohomology theory of a point. So that's your vacuum vector. And every other vector in this cohomology theory is just basically obtained by applying the Heisenberg operators or the Nakajima operators on the vacuum vector. So this is basically this gives you the, again, following the previous formalism, exactly gives you the same thing, except I'm trying to say that for C2 it's much easier. So for C2, when we write down the Gromov-Witten partition function and the equivariant small quantum partition function, we are going to extend everything to this polynomial ring in the character. And so we will be working with functions and variables T1 and T2, and goal is to see how they match via the universal change of parameter. Okay, let us stop in here, and I will continue this on Thursday.
Okay.
Okay, sure. Cheers.
You said Thursday back to the 1 to 3.
Would you like back to the normal time, or would you like this time better?
Depends on depends on when you make the class. I need to make some other choices.
I think 1 to 3 there's another. If I do the other, I think
Okay.
1 to 3 so the other can come.
Yes. Okay. Okay.
So
Okay.
I think
Yeah, I would. Yeah, I'm